I just have a couple quick notes. I want to reach out to anyone that's here that has gone to any of the public nights up on Mount Tam. The Friends of Mount Tam and the astronomy program is going through some changes, and if anyone would like to volunteer to help the astronomy program up there, specifically Tinka, if you could let me know, just email me. I'll put my email in the chat. They need more volunteers, so I'm trying to get the message out to as many people as possible. But as far as club news for the SFAA, we return to our in-person star parties, members only, and those, I believe we have one next weekend. And that's about it for news right now. It's very short.
Okay, thank you very much.
Over to Linda.
Yeah, so I'm Linda Mahan, and I'm going to tell you about the next 2 months' upcoming talks before I introduce tonight's speaker. We always meet on third Wednesday, and March 16th, Ken Lum, who is a longtime friend of SFAA, will be talking about travels into astronomical history with the Antique Telescope Society. Astronomy, more than most scientific disciplines, has progressed only as a result of advances in instrumentation, particularly the telescope. In 1955, 3 years after our anniversary that we're celebrating at SFAA this year, Henry C. King wrote The History of the Telescope. Then in 1992, a group of mostly amateur astronomers established the Antique Telescope Society. Ken Lum will talk about their annual visits to examine great historical telescopes and their other areas of research. And we will see many examples of their amazing experiences. So I'm really looking forward to hearing that. On April 20th, Pascal Lee, founder and chairman of the Mars Institute and the principal investigator of the Houghton Mars Project, NASA Ames, will talk about N-1, alone in the Milky Way. The Drake equation was formulated in 1961 by Frank Drake. It was not so much the quantifying of the numbers of civilizations in our Milky Way, but to develop a way to stimulate scientific dialogue on the topic and an estimate of advanced civilizations in the Frank Drake equation. Pascal Lee will revisit the Drake equation with a new perspective, and that is on April the 20th. Tonight's speaker, Ariana Gleason, Holbr, received her undergraduate degree in geosciences from the University of Arizona in Tucson. There she worked for the Spacewatch project, discovering near-Earth objects, and discovered Comet Gleason. She also has a main belt asteroid 10639 in her name, Asteroid Gleason. She received her PhD in Earth and Planetary Science from the University of California, Berkeley in 2010. She joined Stanford University as a postdoctoral scholar in 2010, and then worked for the Los Alamos National Laboratory in the Shock and Detonation Physics Group before joining SLAC National Accelerator Laboratory as a staff scientist in 2018. Her work focuses on visualizing materials' behavior and response across all length scales at the most extreme environments possible in nature, from the depths of the Earth's crust to planetary cores, and even stellar interiors. Her studies center on high-pressure mineral physics and planetary evolution from the atomic level up. In 2019, she received the Department of Energy's Early Career Award from the Office of Science Fusion Energy. Join me in welcoming Ariana Gleason Holbr as she tells us about shocking origins, meteor impacts, and the chemistry of life. Welcome.
Thank you so much. It is such a pleasure to be here. I'm going to go ahead and share my screen. Let's just make sure we get that squared away. All right, and we'll take the closed captions off. Do the slides look like they're coming through?
Mm-hmm. Looks good.
All right, wonderful. Well, thank you again so much for this really exciting invitation to be with you all this evening with the San Francisco Amateur Astronomers live stream lecture. My name is Ariana Gleason, and I am a staff scientist at the SLAC National Lab over in Menlo Park area in Northern California. And I'm delighted to share with you some exciting work we're pursuing, combining very extreme conditions with that are often considered very destructive with something that is as incredible and as exciting as the origin of life, and looking at this from a really fundamental level. First, I want to sort of give the lay of the talk, the outline. So we'll consider probably many of the hypotheses that you've already heard about when it comes to origin of life ideas. And then specifically, we'll talk about something called the impact hypothesis that focuses on how collisions and impacts of meteors, meteorites, and planetary bodies may actually be one of the main mechanisms to build up the complexity needed for life. And we'll talk about how we simulate these very energetic and rapid, very ultra fast processes that take place. How we actually do that in the laboratory. We watch things explode in the lab, but we can mimic the timescales and the extreme conditions simultaneously and explore some of the fundamental physics. We do that, we observe these transitions by using some really fast, fantastic photography. But basically, we're looking at technologies that have only just come online, maybe in the past decade or so, that are enabling these snapshots of molecular changes, possibly leading to the origin of life during these collisional events. And then we're going to come back and say, you know, considering the frequency of these different events, it could be that life is far more common than we previously thought. So we'll walk through that. So first of all, setting the stage, zooming all the way out, you know, the recipe for life and exobiology and astrobiology, when we think of these different, the complexity required, really we look for key aspects of the same recipe. So we need materials that are suitable for providing the duration needed to build up that complexity at the molecular level and transferring that up. We certainly need the chemistry that's appropriate. So the different molecular buildup from the atoms to very simple molecules to the more complex nucleobases and the amino acids that we need. And we certainly need water. That's another key ingredient when we think about the origin of life. And then to bring all of this together in the appropriate components, we actually need to input energy into the system to kickstart this process. So we need energy. Oftentimes we think of different energy components. Could be the actual suns, as it were, themselves, could be tidal, could be geothermal, but it also could be impacts. And this is where newer technologies that have just recently become available to us can help us to visualize the opportunities in building up life. And considering how frequent there are these impacts and dynamic events in our solar system, in our universe, life is probably far more common than we thought. Now, if we consider the prospects for life, and I think you all have probably heard and thought about this maybe even more than I have, there are certainly hundreds of billions of galaxies in our universe. And the duration of time here that this process, this experiment of life has been able to be executed is very, very old, right? 14 billion years we've had to practice this recipe for life. And moreover, each galaxy during that 14 billion years roughly has over 100 billion stars. Each of these stars is a sun. And most of these suns they have planets or planetary bodies or bodies that could potentially have the right ingredients for life. And since we know that the laws of physics and chemistry are effectively the same everywhere, we can start to look and have a really exciting opportunity to examine these different exoplanets beyond our own Earth. In fact, I was just looking the other day, the number of exoplanets discovered and confirmed is well over 4,000. And of those, if you look in the Goldilocks region of habitability, there are now well over 60 exoplanets in a habitable zone. So to seed life, the origin going from prebiotic to biotic, I think has a few different avenues, different theories we're looking at. And today I'm going to discuss another one, so-called the impact hypothesis. So for life, when we think of the complexity of the molecules that are actually defined as biotic, we have to start and go from very simple up to complex. So simple elements that are very common in our solar system and in our universe are listed here on the left as a starting place: carbon, hydrogen, oxygen, and nitrogen. These are really rudimentary, simple elements that can then form into fairly common molecules. You will be familiar with methane. We probably release some of this every day of our lives. Ammonia might be something you clean with. Water, we're very familiar with in terms of keeping ourselves hydrated. Carbon monoxide, carbon dioxide. These are all the molecules that we might release when we breathe out, but they can come together in different ways. But inputting the appropriate level of energy at just the right moment to go from a very common, simple molecule to something more complex that would be like an amino acid or a base, a nucleobase of RNA. This takes an act. This takes a step forward in understanding how that structure comes about. And I want to pause here for a moment and say that going between these very simple molecules to something more complex also has to do with the handedness, or the way in which these different molecules are coming together will change their function. And we know, in fact, there are up to 70 or so different nucleobases, different amino acids, and you can have different handedness, so-called chirality, right-handed or left-handed. But it turns out that of these, you sort of have a 50-50 chance of being left or right-handed. But of these biologic amino acids that support life, are only left-handed, right? So what are the chances of building up complexity and having this appropriate chirality that reinforces that biotic process? That's hard to see stochastically how that would come about, and certainly an emergent property. But part of what my research is focusing on at SLAC is considering the dynamic processes that would input the appropriate energy into certain systems that would build up that complexity, but also leveraging what we know about mineralogy and sort of the carriers of these really fundamental and simple molecules as they ride along on these sort of solar system Ubers, the meteorites that can fall to a planet. Those minerals are key. They're playing a key role in providing the appropriate surface for something called templating. So self-assembly of a particular orientation of molecular buildup and complexity. And so we know that this is certainly occurring in a number of areas in other aspects of geomicrobiology. but could we leverage this sort of understanding of fundamental mineral properties in the meteorites and take it a step further to investigate this possible origin of life? So you're probably very familiar with the Miller-Urey experiments, which is one of several hypotheses for building up this complexity. Essentially, at its core, you have a hydrogen, water-rich atmosphere. You have the appropriate simple molecules that I just mentioned, and you basically use a bolt of lightning, right? You have an electric spark that stimulates breakdown of these materials, and they will recombine possibly in a more complex fashion. And in fact, in these Miller-Urey experiments that first took place in the early 1950s, they were able to make all 70 nucleobases, amino acids, right? So this is a viable path to get some of this amino acid production sort of kicked off. But the key here is then how do you take that to the next step and encourage continuation of those of that sort of complexity buildup. Another hypothesis that you're probably very familiar with is the notion of extremophiles and leveraging high temperature, differences in toxicity, sort of pH, whether it's very basic or very acidic. We found that we can track in the tree of life effectively all a common branch that shows us that we are all extremophiles. There's like a 60 degrees Celsius or a high temperature original branch that is then shown to be connected to the rest of life. And this could take place in a number of areas. You might be familiar with black smokers or areas in the oceanic crust where you have upwelling of hot and very rich, chemically rich magmatic material. And when those, when that magma is interacting with that seawater, you get actually quite an exciting suite of chemical reactions that take place. And interestingly, a number of very robust biologic environments are possible here in this black smoker. You might also be aware, in different other regions on the Earth's surface where you have high acidity and certainly an interesting variety of chemistry going on, you can still have life persisting. So this is another avenue we've explored. But the one we're going to talk about today in a bit more detail is the notion of impact synthesis for this complexity buildup. So in interstellar space, certainly in our solar system, as we know, there can be quite a variety of different collisions between different materials. You can have dust grains collide. You can have meteorites that are broken components of other asteroidal bodies. They could be primitive, they could be processed, meaning you can have different degrees of heating or cooling histories for each of these. Certainly you can have asteroids that collide with one another, planetesimals, as you are building up the planets that we see today. Their history, their collisional history has been quite dramatic. And the idea is that for all of these different stages of collisions, different molecules, these very simple molecules, can ride along, right? They can be certainly an intrinsic part of those materials. But during that collisional process, when you have an impact event, you generate a shock wave. And these shock waves automatically impart such tremendous energy such that instantaneously high pressure and high temperature states are achieved. During this moment, these simple molecules can break apart and reform, perhaps, in a more complex way. And that's exactly the process that we're trying to visualize here at the SLAC National Lab. So want to take a side note here in considering a wide variety of meteorites that we are excited to study. So as I said, meteorites are these remnant or component materials of asteroids or comets. They can land on any body. They land on Earth. There are certainly lots of impacts we see on the surface of the moon, as perceived by, or is noted by the craters. And in fact, we sweep up many thousands of tons of this extraterrestrial matter. And they're very small to very large. So you can have sub-micron, so smaller than the width of your hair, these particles from micro meteorite impacts that actually generate in an instant, in some hundreds of nanoseconds, very hot molten droplets, right? Oftentimes when we look at our satellites and different maybe components that have a silicon source for energy for energizing that satellite, there's so much impact, debris and pits. And so there are many studies that actually look at the consequence of micrometeorite impacts. And it's just these tiny, very small sub-micron, sub-width of your hair bits of dust and spherules that cause all this damage. But then some of the oldest meteorites certainly are from interstellar dust. You can have a suite of mineral components from very small diamonds, so carbon at the highest pressure temperature. And a really exciting, I think, notion or discovery for a great many meteorites is that they contain themselves the amino acids that are, in fact, the building blocks of life. So we've got, examples from the moon, from Allen Hills. Here we see chondritic material. We've got meteorites from Mars, certainly the Allende class of meteorites, and even Vesta, where we know there's a large metallic component. And so if we consider all the different flavors of meteorites that we have, we sort of classify them into two parts: processed meteorites and primitive. So primitive meteorites might be something like a chondritic stony meteorite that is really from the very oldest meteoritic material that we have from the interstellar mix. And these may have chondrules, very rich in volatiles, calcium, aluminum, certainly carbonaceous chondritic meteorites are really exciting because their carbon content is quite high. Then you have the processed meteorites, and that's sort of shown here on the right, wherein these can be components, fragments of other larger bodies. And what that means is they've undergone some high pressure, high temperature process themselves. So iron meteorites, which Linda referred to earlier as a component of her jewelry, these are very iron rich, probably remnant cores of other differentiated bodies. In fact, I'm working with a colleague who they're a PI on looking at the iron asteroid Psyche. And that has a wide variety of topography, believe it or not, on this this very metal-rich asteroid that they're going to look at with their satellite when it's deployed. So iron meteorites, and they often have, if you look at them in cross section, they have these beautiful lamellae. The iron nickel lamellae have exsolved from one another during this heating and then cooling process. And so they have these really beautiful linear features called Widmanstätten lamellae. So that's often seen in these iron meteorites. Then you have a suite of other meteorites that are often a mix of different compositions. So-called Palestine meteorites are fascinating. They have a component of this iron nickel rich metal that has clearly been molten at one point next to material that is rich in various silicates. So it looks a lot like our Earth's mantle. And what's fascinating is within a certain region of some of these Palestine meteorites, there are mineral phases that on an equilibrium, thermodynamic equilibrium phase diagram are impossible to put together, right? So again, a wide variety of mysteries. How do you get volatile rich inclusions in the silicate olivine grains that are right next door to something that's clearly been molten iron, right? These are mysteries we continue to pursue with the technology we have today. And then certainly there are achondritic, very stony, crustal-like meteorites that we can also capture. And these different meteorites, they move around. Certainly they're, a wonderful way to transport material from one part of a solar system to another part. So I like to think of them as the solar system Uber. And incredibly, even the Murchison meteorite that we'll show here in just a second, this one is a photograph of the Murchison meteorite, which actually contains all 70, a wide array of these amino acids that are critical in setting the stage for life. And so really thinking about the sequence of what we're able to observe and identify in the meteorites that fall to Earth, and understanding the gap between where these materials started in the interstellar medium, and then being able to provide the energy input to build up that complexity such that it's packaged already in the meteorite itself. That's just really exciting. But I think the last piece that part of my research focuses on is this notion of templating, that the mineralogy matters, that the materials in the meteorite itself matter when you're trying to build up this complexity to go from very simple to more complex minerals. And some of these minerals you're probably familiar with: limestone, calcium carbonate, clays, kaolinite, montmorillonite. These are clays you often find in cement or as a production of cement. Silica, that's around us. It's probably on the front of the computer that you're looking through now to see me. Certainly alumina, this is like ruby effectively, and different aluminosilicates and titanium oxide. In particular, my research focuses on how iron and titanium bearing minerals can be leveraged as these key in templating. So if we look at previous work in this area where we're thinking about the impact hypothesis, there was an interesting study in 2014 by Ferris et al., where they started with a really simple molecule called formamide. So this is hydrogen, oxygen, and nitrogen. And it's actually quite abundant in interstellar clouds. And it turns out that if you decompose or pull apart, tease apart different aspects of this formamide, you're able to have these very simple molecules, these building blocks, that then can reform into nucleobases. And so the initial study here looks at inputting energy into this system by using a very high power laser to generate a plasma state. And so what they did is they took this formamide sample and they subjected it to a high power laser that actually generates this laser induced dielectric breakdown, where these molecules, these bonds in the formamide actually break apart. And so what we want to do, what we want to tackle is taking this formamide and subjecting it to really extreme conditions and observing the consequence on ultra fast timescales. Because part of the interesting aspect of the Ferris study is that they did observe that nucleobase buildup, but not at timescales that allowed them to watch exactly how these molecules were forming together. So we generate high pressure in the laboratory in a bunch of different ways. We have many tools. You might think of high pressure in your own house, possibly with soda or carbonated beverage that you might have. And that CO2 is held in place in that beverage by actually applying a slight pressure. That's why you hear that release of the CO2 when you open the can. Certainly different natural events, you can achieve very high pressures at the bottom of the ocean floor. This is, several atmospheres at that point. By the time you get to the center of the Earth, you are 3 million times, over 3 million times our atmospheric pressure that we have here on the surface. So you increase rapidly increase in pressure as you go down within the Earth. Certainly that changes when you have even larger bodies. If you're talking about Jupiter-sized planets, even going out to stars, very small to medium-sized stars, up to very, very large stellar bodies. And so below here, I have sort of the suite of tools that experimental physicists have at their fingertips. Something as simple as a tabletop pressure vessel. You can apply tonnage, several tons to a small volume, a small surface area that allows you to achieve very high pressure. There are different devices called diamond anvil cells, but then part of my work is focusing on laser-driven ablation, which then generates a very high pressure state. And we'll walk through that here in just a moment. But we have a lot of tools. We can make things explode and study the consequence of that highly energetic and dynamic process with a suite of probes. So we can track the atomistic response. We can follow at the atomistic level how these materials are transforming in real time. Okay, so our study here sort of focuses on this middle pressure range, as I've shown in this slide. So I've alluded several times now to the fact that these processes occur on a rapid time scale. In fact, supersonic, right? So faster than the speed of sound, which implies you're actually generating a shock wave within your material. And this view graph is sort of a cute way of considering what does that mean? You have a choo-choo train, you have some sort of on its track and it's going along spaced appropriately. But let's say something happens. There's a braking issue on some of the cars. And so you immediately and instantaneously lock up some part of the region, which means behind it, you have a buildup of material. You have a buildup of these different train cars. This propagates forward in time, this buildup of material or buildup of train cars, until you cannot compress anymore, and the material has to respond in a certain way. Oftentimes, it responds by transforming, undergoing some process at the atomistic level to relieve that stress. Moreover, at the end, you might consider how a set of train cars first bump into each other, and then there's often a release or an extension process on the back end. And we see that, in fact, in condensed matter as well. So think of a shock wave as a supersonic process that transits a material, and it causes a set of very discrete and reproducible mechanical changes in the material. So that's great. It's cool. It happens in materials during these collisional events. But to witness moment by moment, atomistic atom to neighboring atom, what's going on, often, say for the past several decades, it's hard to resolve in time something that's taking place that quickly. It's a little bit like from Stanford, certainly Muybridge and his tripwire for photographing the galloping of a horse. It's a little bit like, let's say you have a bet like Muybridge did, and you want to find out, how does a horse gallop? Do all the hooves come off, or maybe one stays down? But if you only have a camera that operates at a certain speed, a slow speed, you may just capture the beginning and the end, which doesn't really give you all the appropriate information. In the same way, you have a collisional process that takes place between two bodies. There's a lot of rich and rapid chemistry that takes place. But if you don't have the right shutter speed on your camera, you're going to miss it. You'll see the beginning and the end. And it doesn't give you that information that you need. So we can leverage here at SLAC a very high-speed camera. And we're able to visualize all the exciting things that happen in between. So just for the Muybridge horse galloping bet, it turns out that he made that bet, all of the hooves come off. And so he had to leverage that in resolving the details there. So just like Muybridge and the camera and the tripwire spaced just so he could take snapshots of the horse galloping, I have to have a camera just so I can watch at a very high, a rapid time slice how these atoms are changing during my dynamic process. And so a few terms I'll introduce here. Something is a nanosecond timescale. So nanosecond timescales, this is the time duration over which you can have a shock compression event. Now it can last then much longer, certainly when you have large planetary impacts, impacts that form moons like our own moon and the like. This can happen over a longer time scale, but that initial material response happens on nanosecond timescale. So what does that mean? It is the distance light can travel, or light travels in a foot in 1 nanosecond, right? That's one way to think of it. Also, you might be familiar with your own computers are often gigahertz speeds, right? Computing process. So a femtosecond, which is how fast my camera happens to be here at the Linac coherent light source, the LCLS at SLAC, that shutter speed is a femtosecond, which is 1,000,000 times faster than a nanosecond. So I have to leverage that sort of speed in order to witness how these materials are changing. So here's a bird's eye view of the LCLS, the Linac coherent light source. And you'll notice, in fact, it goes right underneath the 280. So next time you're traveling around Palo Alto, Redwood City area, you might imagine there are photons below your vehicle traveling 1,000,000 times faster than your computer can run. So it's quite remarkable atomic scale camera that we have access to. And it has a lot of unique properties, and I won't dwell on this too much because I want to keep track of time, but it's very bright. So it's a very bright source of X-rays that allow us to see exactly how the atoms are getting rearranged. It has another unique property that all of the photons that we get to use at the end station are all in phase. In other words, the X-rays have laser-like properties. So they are brilliant, they are coherent, and they are appropriate for the studies that we want to complete here. Okay, so now I've got my fast camera. That's great. I've got these femtosecond X-ray pulses, but I need to combine that with the ability to generate an extreme state, right? I need to generate that shock wave or that collisional process. And so I do that by introducing the X-rays to my chamber here, which is able to deliver very high power lasers. So these are lasers that can provide enough energy as is in a bolt of lightning. So if you see the Back to the Future movie, 1.21 gigawatts. So this is how much energy per surface area or volume that is required to generate a plasma. That plasma then launches a shock in my material, and then I can probe at just the right time with the X-rays. So this instrument is called the Matter in Extreme Conditions instrument, and it's one of many instruments that are available to folks at the SLAC National Lab. So when I generate this shock wave, how does that actually take place inside my chamber? Well, first of all, it all goes back to Newton's third law. For every action, there is an equal and opposite reaction. So let's say I've got my samples here. Let's say I take a slice of meteoritic material, and here I've got these two lasers that are coming in, impinging on my sample. And what happens is that as that high power laser impinges on the sample, I actually generate a tremendous state difference between the ambient condition material and this material. And in fact, I begin to ablate. I generate a plasma, and that plasma ablates, and debris starts to essentially flow off of the surface. So if we zoom in a little bit, you see some of these bits of debris. This plasma is forming, this high energy density state is forming, and debris is flying away. As this plasma is formed, due to Newton's third law, I generate a shock wave. It's like a rocket effect. I generate a shock wave that actually moves inward. And this graphic should show these shock waves move inward, and I generate a shocked regime. So here, these blue dots, just to reinforce, these blue dots maybe are a periodic array of the atoms in some lattice material or some rock, some meteoritic material. But when that shock wave gets launched, that material compresses at this very rapid time scale. And so the atoms come close together. But what can also happen as a consequence is there's actually a phase transformation. Okay, so we generate this new state of material, and then we send in this red beam is supposed to be the X-rays. And then I can visualize using a suite of diagnostics what this new state is. And so then I can come up with a model, a material model of what we're actually generating. So to pursue this planetary exobiology study in looking at the impact high synthesis, I'm going to use 3 different kinds of probes with my atomic level shutter, femtosecond laser, X-ray laser to probe at just the right moment. And so these 3 different techniques, we'll look at X-ray imaging, I'll look at X-ray spectroscopy, and X-ray diffraction, and they each give me a different piece of information. The X-ray imaging actually tells me how these very simple molecules, these volatiles within the meteorite, are actually responding during that compression event. And we can model some of this response by looking at these images. The spectroscopy tells me a key piece about the chemistry, the dynamic chemistry, how the starting material, let's say in this case, the formamide, is actually breaking down momentarily, maybe into different carbon-rich end members, and then reforming into more complex material later on. And then the X-ray diffraction will give me a notion of how the minerals are interacting with the volatile component, the minerals within the meteorite. And in particular, what aspect of templating is taking place during that very rapid time scale. Okay, so imaging a shock wave is actually much like how we leverage imaging in the medical arena that we may encounter if we have a broken bone. X-ray radiography is a really wonderful tool for seeing the inside of different materials, much like we see inside our own body. And in this way, we're also able to see inside a shock compressed material. So here's some work from a student, Brigham Young University, we worked with. And so in these sets of images, let me just orient you here. There are 4 different time slices. So here is an example of a material in which I've placed a synthetic void. So this is a starting place for when we would then have volatile rich material, that formamide, sitting inside of our meteoritic material. And then we send a shock wave. So the shock is going to move from the top to the bottom in each image. And so you can see here I'm taking, again, these nanosecond time slices and taking pictures effectively with the LCLS to image the response of the void and the material inside the void as the shock wave transits. And so here we see that the front of the shock wave has moved through about halfway or maybe a quarter. Here it's about halfway, and then here it's actually quite hard to see. It's all the way through. And so these are some of the early studies we completed just last year in our starting materials. Next, we want to leverage spectroscopy, which will tell us exactly how the formamide in particular is breaking down. So part of the novelty of LCLS and LCLS2, we don't have very crafty naming schemes for when we have certain upgrades. So we start out with LCLS and now we have LCLS2, which is remarkable in a few different ways. It's able to operate at even a higher rep rate, so even faster than we started with. So this gives us access to dynamics, chemical dynamics that are really important at the very beginning of a chemical change. And we can send in something called soft X-rays. So typically for rocky materials, for different aspects of condensed matter, you use so-called hard X-rays, where the wavelength is just so you can, it's very similar to the length scale of the atomic bonds in that condensed matter. Whereas soft X-rays are a different wavelength that give you sensitivity to the molecular bonds. And there are a suite of experiments we will complete looking at formamide under shock compression so that we have access to the visualization of the bonds breaking and reforming. And part of the LCLS2 novelty is that we're going from a traditional copper linear accelerator that has a certain parameter operating space that is a bit slower and a bit less stable, but still very functional, to superconducting linear accelerators. So we're using cryogenically cooled niobium, which is just coming online. We've got a number of experiments that are actually going quite well using our superconducting LINAC. And here we're going to move from 120 pulses per second, so a hertz, 120 hertz rep rate, and we're going to jump up by 1,000,000. So we're going to go to a megahertz. So there's a lot of different paradigm shifts that experimentalists have to sort of consider in jumping up in that much data, for sure. But this will allow us to visualize dynamics, chemical dynamics that are taking place at these very critical ultra-fast time slices. So the spectroscopy component can be considered much like you think of fluorescence. So we're going to send in these very short and rapid X-rays into our meteoritic material that contains a formamide, and we're going to look for a color difference. So a certain color of X-rays goes in and a different color comes out. And that color difference, that fluorescence that we see, we'll be executing these later on in this calendar year, in fact, will tell us a great deal about the chemistry. And finally, the diffraction. So every single material, every single mineral has a very unique atomistic packing. And this packing can be identified easily by looking at something called the X-ray diffraction. So it's like a mineral's fingerprint. Every single one is unique. And so we're going to track how this fingerprint changes during that shock compression event to examine the templating aspects of mineral templating aspects of this study. And I've done quite a bit of work already on silicates, actually looking at the consequence of impact events on minerals that are common in the Earth's crust. In particular, I've looked at quartz, I've looked at feldspar. These are minerals that are the most common minerals in the Earth's crust, are these silicates. And I had a study several years back that looked at step-by-step how these X-ray diffraction patterns change. And so part of the work is done in these large laser laboratories. And so here's just a photograph of an early study that I did. We've got these large optics that are able to focus our laser. The entire platform here at MEC. Here's a person for reference here, but it's about the size of a person. The chamber's 2 meter in diameter. Here's the interior view. And so you're able to get in there and crawl around and position your detectors just so in this 2 meter chamber. And we can visualize, we can actually record what happens to a sample. So here we see actually no diffraction. These are artifacts, blemishes in the detector. And when we send the shock wave at a particular moment in time, a few nanoseconds later, in this case, about 12 nanoseconds later, we see what's actually really exciting. The atoms have broken apart, the bonds, I should say, between the atoms have broken apart and reformed in a fundamentally new way. This is called a reconstructive phase transition. So the bonds in glass, actually between silicon and oxygen, have gone from a tetrahedral four coordinated to an octahedral. This stishovite mineral is often found at impact sites. Well, I shouldn't say often. Actually, by volume, it's found not quite as much, but it is a signature. It is a shock, a barometric signature of an impact process or a high pressure dynamic process has taken place there. So we hope to apply these sorts of experiments in investigating the origin of life. And I've hoped I've convinced you that these are really exciting studies. And we leverage a suite of these ultra fast time slices to watch and hopefully give new light on the opportunities for impact synthesis to be one of the pillars, perhaps the pillar in considering how life has seeded, certainly here on Earth and maybe elsewhere. And I'll say that the opportunities for investigating the appropriate recipe for life all across our solar system and the universe is exciting. Of course, the new results coming back from Mars sample return mission is certainly underway. There's lots of new and exciting information coming back from different icy moons where that appropriate recipe of minerals and water is prevalent. And it's very much pointed to that opportunity, that notion that, you know, life may in fact be far more common than previously thought. And with that, I certainly have a whole host of collaborators and researchers as part of the team for this project. Certainly folks at Stanford and SLAC, as well as other institutions, national laboratories, and academia. And with that, I thank you for your attention and welcome any questions. Thank you so much.
Wonderful. Thank you. Thank you very much for that presentation.
Yeah.
Well, we are open for questions. If anybody would like to raise their hand or speak up or type into the chat. And
can I be heard? This is Linda.
Yes.
Yes.
Yes, I hear you. Thank you.
Okay. I've been interested in the city of Nordlingen, Germany, which is sitting inside a crater, RIES or REIS crater.
Yes.
And it was discovered that there are tons of diamond under it from the impact.
Yeah.
This is something that I read in the last few years. And that was an enormous change. I guess that was just the heat and pressure that caused that to occur. And they've discovered sand spikes that surround the city. I just read that in the last couple of months. And the only place that they found anything like that was in Southern California from the shock of the impact of the Nordlingen crater. And who knows what else has been discovered there or maybe yet to be discovered there.
Yeah, it's actually quite remarkable. The minerals can tell the story of that very extreme event. And looking at crater mineralogy is actually really exciting. I've studied a number of the minerals, in fact, at Nordlinger crater or the Nordlinger region in the Reese crater. In particular, something called plagioclase, which is feldspar is common rock in German, but feldspars are the most abundant mineral in the Earth's crust, and they undergo very specific changes in the microstructure. So you go from a crystalline material, something you might see in a thin section, to an amorphous material. It actually turns into a glass, and the point at which it undergoes these changes tells you exactly the pressure and temperature condition, and you can work out the size of the impactor based on the mineralogical evidence, which is really exciting. And I think you can do modeling certainly based on the diamond formation at depth, different aspects of the sandstone, like you mentioned, different changes in the quartz or the sandstone rich layers beneath, that actually allow you to chart out step by step how that impact changed the crustal rocks, which is really exciting, right? Because nobody was there during that process, but the minerals hold the clues. And I think that's so exciting.
We have some questions coming in. Philippe asks, is it correct to assume, sorry, the chat moved. Is it correct to then assume that life depends on chemistry? And if so, what is the temperature range that can accommodate the necessary chemistry of life?
Oh, that's a great question. I'm definitely not a biologist. So I'm more of a geologist, geophysics by trade. With respect to the chemistry aspects, I think some of these initial steps that enable this complexity buildup are actually at very extreme temperatures, many thousands of Kelvin, which would be also many thousands of degrees Fahrenheit, as it were. But just for a momentary period of time, they're short-lived bursts of high temperature sort of environments. However, if you look at and do some investigations in the extremophile hypothesis for origin of life, there's actually quite a few microbial materials that will easily thrive at these black smokers in the Earth's in the oceanic crust, where that crustal material has a magmatic upwelling. And those temperatures are actually quite hot for longer periods of time, many days, months, years. It can sustain this magmatic activity, and the temperature is quite hot. So I think the key question is, for origin of life, how do you kickstart it? It could be very momentary and many more thousands of Kelvin hot. But actually, to sustain life, right? Not just to have a one-off event, right? So you have one amino acid, okay, great. But actually this continuation and enabling reproduction, right? And multiplication of this amino acid, it's probably more metered. But like I said, I'm not a biologist by trade, but that's certainly sort of where our studies are showing, yeah.
Thank you. We have a comment that simply says, thank you so much. Fascinating, and appreciate your giving us a peek into your research.
Sure.
And then we have another question. What are the big projects that SLAC will be looking into for the rest of the decade?
Oh, that's a great study. A great question. I think there are a number in the materials, condensed matter, and atomic level studies. We are fascinated by emergent properties. So, and life, or origin of life, is probably one of these emergent properties. So, aspects of matter transformation and beam or energy matter interaction that are stochastic, right? That are one-offs. But in order to visualize, and they might be remarkable, right? Because it might be like the seed of life, but you have to catch it at just that right moment. And so having the tools at your disposal to explore emergent properties in materials, of which this is just one example. Another example might be high temperature superconductivity. So let's imagine we have a different energy, a different clean energy source that could enable us to remove our dependence on fossil fuels. There are novel materials out there that will likely enable that, but we haven't found that right combination of structure and property and history or time scale of that material that enables that novel property. I think another area where folks are really excited is still pursuing clean energy in a bunch of different ways, whether that's in battery technologies and optimizing the different chemistries that, for instance, might be at play in your lithium rechargeable batteries, or even in the opportunities for harnessing effectively the sun in a box, right? So realizing fusion energy. So this might be, you might say like, hey, wasn't that a scene in what was it, Spider-Man, right? And Octavius, right? He's got the sun, right? But we are able to do that now. We are able to push toward understanding the physics of fusion as a way to exercise a clean energy technology. But a lot of these different pieces are so complex, so you need the right technology to enable that achievement. So I think that's where we're going. Oh, yes.
We have a follow-up question.
Yes.
David asks, can we mine the moon for precious chemicals and minerals?
Probably yes. I don't think like right now we can, but I'm sure there are, public-private partnerships or private industry that is already gunning for opportunities to extract some of these rare earths that are actually certainly a critical piece in our technology portfolio across the globe, right? We need a lot of these different novel metals and materials that we use in our technology, our cell phone and our computers and whatnot. So probably we'll get there. I don't know like date and time, but I'm sure folks are already thinking about how to extract what we can.
Very good. Philippe asks, so the building blocks may require extreme conditions while the establishment of life may require more moderate environments?
Yes, that's well said. I think that's sort of what the recent studies are showing. There are also additional considerations, the oxidation state, effectively how much iron was at the Earth's surface and for what period of time, and how did that mediate the oxygen or nitrogen levels in the early atmosphere of the Earth that would then encourage continuation of the life process. So I would agree with your statement.
We have a question. Have you looked into the possibility that elements other than carbon could play a similar role that plays in organic chemistry?
Like silicon.
Silicon.
Yeah. So my research has not specifically pursued silicon as one of the sort of backbone elements in the life process and the buildup of the chemical complexity. But what I have looked at quite a bit is silicon in its role in the mineralogical sense, and the different ways in which it's actually quite interesting in the different phases and states it can take at conditions that we're sort of used to, but then also at these extreme shock compression conditions. So I think building that in to having silicon be a major player in the organic materials is probably coming, particularly as I see the minerals as a main important component, as sort of pulling on that thread a little bit more. So certainly do, yeah.
This is Linda again. I have a question, if I may.
Sure.
I know that you knew about how busy it is in Tucson when the mineral show is on in February.
Yeah.
One year, maybe in 2013, 14, 15, we bought a piece of Nantan meteorite. And at first I thought they've ended up showing things that weren't real. And these are small, have very crystalline faces, shapes rather, and bright. And so I questioned it. And then later I found a very large piece that had been sliced like you would slice a large piece of bread. And inside were embedded these crystals in their shapes, deep inside an otherwise rather smooth kind of surface of a Nantan meteorite. And I've always wondered, how did they arrive in there and stay in such highly textured, almost, I don't know. I mean, they didn't look like they'd been melted or smushed or altered. They had incredible shape, and yet the mass around it and between them was smooth. And I have no idea how that could happen.
Yeah, no, that's a wonderful question, and it gets back. It also ties in well with the Palestine Meteorite class, where you can see different phases, where like from traditional thermodynamic equilibrium phase diagrams. So how we understand, solids that then melt, or different phase transformations, for carbon, graphite, diamond, and the like, or for ice, right? Hexagonal ice, like it's in your freezer, to various exotic high pressure phases of ice. All of these different things. We have a notion of how the periodic table works under sort of standard pressure temperature conditions. But as you squeeze on these materials, as the atoms are forced to come closer, and you're actually having an interaction, not just the outer electron, electron cloud of these different atoms, but as you actually squeeze tighter and tighter, the response is we're not able to predict them very well. There's so much we don't know. If you were to take the entire periodic table and subject it to high pressure, you would actually reform how our sort of paradigm of thinking in terms of chemistry and interaction. So that is to say, we don't know. We don't know how these different phases can momentarily coexist and then have that frozen in for long periods of time. That's part of this exciting research that we're doing at, high pressure, high temperature, shock waves, diamond anvil cells. We have all these cool tools, but we don't know. There's not one sort of key, piece of evidence. Every single element, every single material might be behaving a bit differently. So it's a wonderful question. That's why we need researchers and folks to continue to study it.
Well, I was imagining that they were trapped within, but as you were speaking, I thought that maybe they could have been created within rather than trapped within from an external source. So so that would be very, very amazing to decide how that happened.
If you could have that right along with that atom eye view, right?
Right.
We got a comment on YouTube. It's not much of a question exactly, but it says the DNA polymerase enzyme used in PCR works at like 100 Celsius, and that we took from an extremophile.
Yes, I mean the extremophile hypothesis is very exciting, and like I said, I think our branch of the tree of life can actually be traced back to something that is stable clearly at high temperature. So somehow we're all part of that high temperature extremophile origin. Yes, sir.
Philippe asks, does your research consider it a possibility that the that the primordial molecules of life could be radically different than the ones we find on Earth? Or is it that the periodic table, being a universal constant, what we observe on Earth must be close to the norm throughout?
Oh, that is a great question. I'm not sure. I think we don't have enough experimental evidence to try to parse that out. I think the tools we have, the technologies we have are ever evolving. And the tools I have today will be very different than what we have in probably 50 years to explore, the periodic table at extreme conditions. And I think our understanding of stellar interior, of fusion, of a lot of these really fundamental particle physics components that then are the genesis for how we would then construct an eventual set of different elements is also evolving. And in particular, there's a lot of really novel work going on in considering the symmetry aspects of particle physics. And that chirality I mentioned when it comes to these different nucleobases. There's also a handedness, it turns out, and I'm not a particle physicist, but there's a handedness in certainly in studying many different kinds of particles in high energy physics. And so I don't know, it could be that the periodic table is the norm. I sort of doubt it though, by sheer volume of the different kinds of extreme states of matter there are in our universe. We're probably unique in having the periodic table at the Earth's surface that we have it at. So I think that's really exciting.
Well, if there's any more questions, feel free to unmute yourself and ask, or type it into the chat. Philippe says, fantastic. Thank you.
Yeah, thank you. Very, very great questions.
Well, Linda, what do you think?
I just saw somebody had a message to me and it blanked off really fast.
Oh, I didn't see that.
Yeah, somebody had a message to me, so. It's gone. It was just there for a second and it was gone. Okay.
Well, feel free to reach out to me. I'm at Slack, so I'm sort of nearby you guys.
Yes, indeed.
San Francisco amateur astronomers. One day I'll come and be able to see you guys in person, I hope, at a future lecture. So
yes.
Or I can come and hear another lecture in person. So I
I'll
certainly thank you for the opportunity.
Thank you very, very much. We've all learned a lot.
Great.
It's good to have you. Thank you very much.
Thank you.
Thank you guys. Okay, have a wonderful rest of your evening.
You too.
All right, take care.
Bye-bye.
Bye-bye.